Touro is a reservoir hydropower plant located on the Ula River in northwestern Spain in the province of A Coruña. This plant, operational since 2008 and managed by TASGA, boasting a gravity reservoir with a capacity of 3.7 cubic hectometers and a maximum operational flow of 60 cubic meters per second. Operating autonomously, it incorporates 2 Kaplan vertical axis turbines, with a total installed power of approximately 12 megawatts. In 2025, TASGA has obtained authorization to install a green H2 plant hybridized with Touro HPP, following a lengthy process that began in 2022. Green hydrogen will be produced on-site through an electrolysis plant with an installed capacity of 0.4 megawatts, capable of produce 67 tons H2 per year, which allows for a significant reduction in emissions compared to conventional technologies.
Where is the Salto de Touro HPP located? HPP integration with a green H2 plant. The green H2 plant is situated on a developed site, which has access routes and is located 90 m from the hydroelectric power station, allowing all the plant's components to be concentrated within a very small area. The electricity supply comes from the hydroelectric power station and is provided via a 6 kV underground power line connecting the 2 facilities, whilst the water required for the electrolysis process will be drawn from the Touro reservoir, connected to the plant via another underground pipeline, at a rate of 0.044 liters per second. The surplus from the process, wastewater, which will amount to 50% of the water drawn in, undergoes treatment prior to being returned to the River Ula. This treatment involves passing the water through an activated carbon filter and a bed of ion exchange resins, resulting in deionized water, H2O. Which are the objectives?
The D-HYDROFLEX project aims to study the hybridization of the Touro HPP to produce green hydrogen that increases flexibility, reduces costs, and is more environmentally friendly. The main outcomes of the project include new knowledge on hybrid power plants, the development and test algorithms for optimal operation, including an energy forecasting model tool, hydrogen decision support model tool, performance degradation model turbine tool, the development of an environmental indicator monitoring process whose targets are to know the behavior of Ula waters along the time, the suitability of its waters to produce green hydrogen, to get a better understanding of environment effects of the HPP's activity and future green H2 production plant.
Testing the algorithms.
The ITG Technology Center has developed an AI-based web application capable of generating energy production plans, optimizing hydrogen sales, and calculating turbine performance in hydroelectric power plants. Next, we will show a practical example in which an operator accesses the application and explores its features. If the operator wishes to generate an energy production plan for the following day, they simply need to select the energy forecasting model and input key parameters, such as the river flow rate and the initial reservoir level. With this information, the application automatically generates a detailed plan for the next 24 hours, showing the evolution of the reservoir level, the turbine flow, and the energy produced. Secondly, the hydrogen decision support model allows for the generation of an optimal plan for the next day, indicating whether it is more profitable to sell electricity or green hydrogen. This model seeks to maximize plant profits while contributing to the decarbonization of the transport sector, as the hydrogen produced is destined for sustainable mobility. Both models consider key variables such as forecasted electricity prices, hydrogen prices, and weather predictions. Additionally, the application incorporates 2 other artificial intelligence models that allow the operator to monitor turbine performance in real time. At ITG, we promote the digitalization of hydroelectric plants, transforming them into more efficient, sustainable, and competitive facilities.
Environmental indicators monitoring.
Field monitoring program. Location key sites. Upstream. Sensor probe and intakes. HPP and green hydrogen plant. Downstream, HPP, discharge channel, wastewater point and sensor probe. Ula waters are suitable to develop a hybridized H2 plant. However, to treat the intake water will be required. Turbidity values are commonly over 1 NTU. pH values exceed 8 units when biological activity arises. There are wide knowledge about the effects of the HPP over a mass water. Breaking connectivity, sediment retention, and aeration waters are the most obvious. In this case, we detect a very local effect associated to turbine's operation that causes a stream from the intakes to upstream, hindering the mixing between waters turbinated and water stored above it in the reservoir. On the other hand, data collected from upstream and downstream probes show a similar behavior on both locations, with offsets associated, the aeration effect, settling effect of the dam, and the stream effect cited above. However, all the observed offsets, O2 concentration, pH, and turbidity, are influenced by the biological activity, green algae and cyanobacteria, that occurs from April to September in the reservoir. So, that activity involves a reversal of the offset values collected by both probes regarding the rest of the year.
Data collected from probes show a similar behavior on both locations, with offsets associated the aeration effect, settling effect of the dam, and the stream effect cited above. In addition, the offsets are influenced too by biological activity, GA and BGA, in the reservoir that causes a reversal of the offset values regarding the rest of the year.
Key functionalities towards innovation.
The demo provided a deeper understanding about the integration of green hydrogen production into existing hydropower infrastructure, developing tools that allow take daily and slash or hourly decisions about production on a hybrid power plant, focusing on electricity or green H2, depending on market conditions and the energy forecasting model. It has enabled us to evaluate a system for monitoring environmental indicators, which has helped us to understand the behavior of the water body in a simple and replicable way, providing the necessary knowledge for the hybridization of the hydroelectric power plant and enabling us to accurately determine the environmental effects and the water treatment requirements for this purpose. Both issues are useful for scalable and replicable hybridization solutions applicable to other HPPs.